Hi everyone, my name is Celine Mahawad and this is my Physics 2211 Lab 4 on oscillations. This lab consists of analyzing the observed and predicted motion of a system in which the mass swings in an arc while oscillating on the spring. I used Tracker, an image tracking software, to record the movement of the mass attached to the spring. I relied on GlowScript, a computational program, by expanding on the starter code given in order to predict the mass's motion. Finally, the position data obtained was used to analyze energy changes through the movement. Comparison of data will reveal how well we can apply physics principles to predict an object's motion. The results show a correlation between observed and predicted data. However, it is not perfect due to the presence of dissipative forces. Let's first start by defining the physics principles used in this experiment. According to the momentum principle, the net force can be calculated by dividing the change in momentum by the change in time. Deriving the second law allows us to obtain the equations for position and velocity. The forces acting on the mass are the gravitational force by Earth with magnitude mg and the spring force with magnitude k times s. Next, the energy principle is used to describe changes in energy of the system. Delta E equals the change in kinetic energy plus the change in spring and gravitational potential energy. In this case, we consider the system as the mass, the spring, and the Earth. No work is done, so the total change in energy is zero. The kinetic energy is equal to half the mass times v squared. The potential energy of the spring is equal to half the spring stiffness times s squared. And finally, the gravitational potential energy is equal to mgh. I began by analyzing the motion of the mass using Tracker. To set the length scale, I used the distance from the attachment point to the center of mass when it is motionless in static equilibrium and set it to 0.7 meters. I chose the coordinate system such that the origin is at the attachment point, and I chose the y-axis to be aligned with the spring with the negative direction of the y-axis pointed downward. I analyzed the motion between frames 5 and 105. I relied on the data obtained to make calculations for my computational model. I noted the initial position vector 0 minus 0.635, 0, and the initial velocity 0, 0, 0 at t initial equal to 0 seconds. The time of one oscillation or period is equal to 1.52 seconds. Using the formulas from the video, we calculate the spring stiffness, which is set to 6.83 newtons per meter, and the relaxed length of the spring L0 equal to 0.123 meters. I made some edits to the starter code. I modified the initial conditions by setting the mass at 0.402 kilograms, the initial position and velocity as provided from Tracker. The gravitational force constant is 9.8 meters per second squared. Next, I updated the spring constant and the relaxed length of the spring as calculated. Then I updated L to be equal to the ball position minus the spring position. L hat equals L divided by the magnitude of L, and S equals magnitude of L minus L0. I computed the energy equations. The kinetic energy is equal to half the mass times v squared, the gravitational potential energy is mgh, and the spring potential is half k times s squared. The total energy is the sum of kinetic and potential energies. Then I updated the force of gravity vector such as the y component is minus mg, the spring force is minus k times s times L hat, and the net force is the sum of the gravitational and spring force. Finally, I had to update the equations of position and velocity by applying the momentum principle. Here are the results for the model after running the program. The graphs represent the x and y position for the observed and the predicted motion of the mass. The curves don't perfectly overlap. The observed mass is slowing down in the x direction and traveling a shorter distance in the y direction. This is due to the fact that the predicted model does not account for dissipative forces such as drag force or the loss of thermal energy. Let's see if the energy principle is satisfied. The energy graph obtained after running the program shows that the change in total energy is zero, reflected by the flat orange line. In other words, the system has no interactions with its surroundings, so the energy principle is satisfied. By estimating the oscillation periods, we obtained a period of 1.66 seconds on the x-axis and a period of 1.52 seconds on the y-axis. The difference between these times of oscillation will create big differences in the spring stiffness K, its relaxed length L0, the spring force, and therefore the net force. This is it for my presentation. Thanks for watching.